Hello everyone, welcome to the operation Let's Fix a Course. I'm going to cover in this video some basics of network theorems, and then I'll move over to Kirchhoff's current and Kirchhoff voltage law. I intend for this to do some practical and some mathematical calculations to prove vice versa, from calculations and practical concept on what we see and how it relates to network theorems, of which network theorems is the technique that is used to simplify and analyze electrical circuits by reducing complex network into simpler equivalent forms. So we'll start off with Ohm's law, just going through the basics and understanding of what Ohm's law is, and then move over to Kirchhoff's voltage and current law, superposition, Thevenin, and Norton's theorem. So to begin with, we'll just start with the simple basics of understanding series and parallel circuits. So within Ohm's law, it states that V is equal to I multiplied by R. So the current, the voltage within the circuit is measured by the current that is flowing within the circuit and the total resistance. In a series circuit, the end of this resistor, which is here, is connected to the beginning of the next resistor. This is what makes them series, and there is no other connection between the two. So the total current will be flowing from this resistor through the next resistor. So that's what makes it series. And the total resistance of the circuit is measured and calculated by R1 plus R2. And then moving over to parallel circuits. So what makes them parallel is that when the current, which is current IT, is flowing into this node, it will thus split into two ways. Then I total is measured by I1 plus I2, and that the resistors are connected such that the beginning of this resistor and the beginning of this resistor are joined into one connection. And then the end of those resistors are also connected at one point as well. Thus, they are parallel. And the voltage across them would be the same voltage, because if you look at the supply over here, this voltage will be sitting exactly across this point and that point over there, thus making it the voltage. I'll write it here. Voltage T, which is the total from the supply, is equal to VR1, which is equal to VR2 as well. And the total resistance of the circuit is calculated by 1 over RT is equal to 1 over R1 plus 1 over R2. These are only the basics of understanding Ohm's law. And within the first series circuit we had, the total voltage is calculated by the voltage across VR1 plus the voltage across VR2, which will give us our total voltage over there. Because as current moves through there will be a volt drop that is across each individual resistance. And then if we move over, before we move over, I'll stop sharing my screen such that I want us to do an exercise. The exercise will be covered just understanding how the resistors work in a complex network, because we are dealing with network theorems, which network theorems is the concept of making circuits into the simplest form in which we can be able to measure. So we have here this example. We have this circuit. So the task for us here is such that if we were to put a multimeter between point A and B, and then we were asked to measure the total resistance of the circuit, what the value would be in that case. So for us to be able to determine that is such that we look at this towards this direction. If we look at it in towards this direction, we can see that, okay, it's a bit complex because of this section over here. We're gonna call that section E and section B. So we just have to redraw this circuit in a way that we can analyze a bit better. So if we redraw it, we have point A over there and B. We have resistor 1. We have resistor 2. And then we have resistor 3. But for this section of resistor 4, I will just extend that point such that it is drawn in this manner. That's our R4. It's still the same circuit, but redrawn in a different manner. And then we also have from that point R5. R5 is also connected here. This is R5. So from here to there is our point B. It's still the same circuit. So we're going to attempt to do the same thing at the top. We're just gonna drag out this point because our resistor 6 is connected at the end of R5, which is, this is the end of R5, and then it goes up. So this is 6. And then at the end of R6 here, we have another R7. And then there is R9 that is going to point A as well. So we're going to extend our point A and draw a resistor that is connected to point A, which is R9. And then we have R8 at the top. This is R8, 8 in series with 10 over there. This is 7. So this whole section over here, which connects R9, R6, and R4, it's represented by our A, which is this A over here and that B over there at the bottom, of which if we have this, let's say this is C. C would then connect 7, R7, R9, and R10. There it is, R7, R9, and R10. They are still connected to the same point. Now, at least when we draw it like this, we can analyze the circuit a bit better, in the sense that we can calculate the total resistance and make a small equivalent circuit of it. So R8 is in series with R7. If we add the two, we will then be left with a circuit as simple as this. Because we've added two, we will have a series circuit of R8 plus R10. And then R10 and 9 is now in parallel. And then we would then calculate. This is R series for this parallel combination. And then we are now just eliminating or calculating the series and parallel combination of the two. Then this resistor over here would be the series combination of R8 and 10, and then the parallel of R9 and that series combination, and then we would be left with this resistor value. We won't be doing calculations at this point, but we're just doing a circuit analysis. And then that series and parallel combination will now be in series with this. All we will need to do is add the two, and then that combination will thus reduce our circuit in this manner, such that we will be left with this type of circuit. And then this would be in parallel with this, and we continue that and so on until we have this circuit. Currently, the naming isn't that much important, but if you follow how a circuit is being reduced, because now as it is, we have the series combination of these two, and the series combination is in parallel with R4. Once we are able to calculate that series and parallel combination, we'll be left with a new resistor there, and then it will thus reduce our circuit, because we are aiming to make an equivalent circuit. And then this R4 with parallel with all that resistor over there, it will be now in series with R3. Once it is in series with R3 and you calculate that, our circuit will be reduced into an equivalent circuit like this now. Then If you look at it, this and this, they are in parallel. And once we calculate the parallel combination, we will thus be left with this circuit. And then I will name this R2 equivalent of everything that we had removed there, which is now series with R1. So R1 plus that value we would have calculated will be equal to it will be equal to our equivalent. Then our equivalent circuit now using this Ohm's law will be in this manner. This will be R equivalent. And then this is what, when we are using the meter, the meter will be seeing this exactly this, and then it will be able to measure our value. But using calculation, this is how we would then analyze this particular circuit. It was an example. So now I'll stop sharing and go back to our slides so that we can do a bit of KCL, Kirchhoff's current law. Kirchhoff's current law is, it has two rules. It states that, the first one states that current entering a node is equal to the current leaving the node, and that an electric charge does not accumulate at any node in a circuit. This is what it means. So if we have a node here, if current flows towards that direction, I1 plus I2 is the total because they're flowing towards that node. And then these I1 and I2 are thus equal to the currents that are leaving the node, which is I3, I4, and I5. So one thing to note once more, and then we'll look at an example. Current entering a node is equal to the current leaving the node. That's the formula. And then no electric charge accumulates at any node. So I will open my presenter whiteboard such that we can look at an example. If we look at this example here that I have pre-drawn, this is what is given to us. If this is what's given to us, we have two known incoming currents. We have I3 over here, we have I15, 15 amps flowing in there. So here in this section, we are given a current of 8 amps, which is flowing in that direction. It's flowing in that direction, which is away from that node A. We have node A, so 15 amps is flowing and 15 amps is leaving that node. Therefore, if we were to calculate this I2 over here, it would have this direction also flowing away because the total of this 15 minus 8 over there is at least the bigger current. Therefore, I2 would be calculated as 15 amps minus 8 amps, which is equal to 7 amps. So 7 amps is our I2, and it has that direction. For this exercise, we need to determine the direction as well based on what we are given. If you look at it over here at point D, 8 amps is flowing towards that node D, and then we have 5 amps even. Then I3 would be flowing in that direction as well. Therefore, I3 is equal to 8 amps minus 5 amps, which would give us 3 amps. So that is our I3 over there, which is equal to 3 amps. So now we know I3 is flowing towards that direction of node C. Then now we need to determine what is the direction of I4. So if you remember the law of KCL, it says that no current accumulates into a node. Therefore, if I2 is flowing towards the node and 3 amps is flowing towards that node, I4 won't be flowing within that node as well, so it's taking this direction. Therefore, I4 is equal to the sum of I2 plus that 3 amps. So I2 plus 3 amps, which I2 we calculated it as 7 amps. 7 plus 3, which is equal to 10 amps. That is our I4. Then if we now have 10 amps flowing towards that direction, I3 flowing that direction, it won't accumulate into node C. It needs to at least flow away from it. Then I1 is flowing that direction. So I1 is now calculated as I3 plus I4, which I3 is given as 3 amps plus I4, which is given as 10 amps, which is equal to 13 amps. So this is how we would then analyze the circuit using KCL. Current that is leaving a node is equal to the current that is entering the node, and that no current or electric charge accumulate at any node. So for this video, I'll end off here, such that within the next video, I will have an exercise whereby we will be doing calculations for Kirchhoff's voltage law, and then move over to some practical component for that same electric circuit, such that we prove our calculations using the practical concept. Thank you.